And now with Dr. Ameer Mohammed, who is Assistant Professor at the College of Engineering Department at Kuwait University. He's going to talk about cybersecurity, implication of quantum computing. Go ahead, Dr. Ameer.
Thank you, Aisha. Let me just share my slides, because hopefully you can see my slides now. So, assalamu alaikum, everyone. Good afternoon. My name is Ameer. I'm really happy to be a participant in this conference as a speaker. And here I will be talking about the cybersecurity implications of quantum computing. And if you're wondering what this means, worry not, I will explain that in a moment. And for the sake of brevity, I will gloss over some details, but that hopefully should not affect the general ideas that we're trying to convey. The goal for me here is to expose you to this evolving paradigm of computation and discuss its ramifications on security. Okay. So in recent years, we've seen a lot of emerging technologies such as AI, blockchains, 5G communications, that all had some effect over the cybersecurity landscape in either a positive or negative way. Now, what I will look at today is arguably one of the less talked about technologies, quantum computing, and explain how it can be a potential threat to some of the elements of cybersecurity and what we can do about it. So, what is quantum computing? In order to understand at a high level what are quantum computers, it would help to look at classical computers, the ones you are familiar with, and try to compare them with their quantum counterparts. So in classical computers, information is represented as a series of bits that can either be 0 or 1, like this. And they are physically represented as a low or high voltage signals that look like this, right? So either 0 or 5 volts. And these voltages, they pass through semiconductor MOSFET transistors, of which more than 1 billion make up this central processing unit that is found in common modern day PCs. And by arranging thousands of such CPUs, we can construct a supercomputer, which can be used to solve really complex problems in a reasonable amount of time. Okay. And so quantum computers, on the other hand, are based on the fundamental rules of quantum mechanics. Here, information is not represented in bits, but rather what we call qubits, which act as a superposition of the 0 and 1 states, a mixture of a 0 and 1. And they're represented using this funny looking notation where Q0 tells us the chance that this qubit is 0 and Q1 is the chance that this qubit is 1. Now you can think of it as a bit that is yet to decide whether it should be a 0 or 1. But it's a mixture of both, but once we measure it, it's either 0 or 1. And unlike normal bits, qubits can actually be correlated with each other. So for 2 qubits, we are able to express them as follows with a mixture of not 2, but 4 different possible states. And the state of 1 bit is dependent on the other. This correlation is due to what is known as entanglement, which is another quantum mechanics principle. So superposition and entanglement are the central elements that distinguish them from classical computers and enable them to solve certain problems more efficiently than classical computers. Because we can express this information in a much larger, richer space. So what does a quantum computer physically look like, right? We know what a normal classical traditional computer looks like. What does a quantum computer look like, right? We want to see what it looks like. Let's consider Google's processors, which were developed in collaboration with UCSB, University of California, Santa Barbara. So these processors consist of between 54 and 72 qubits. And here is a qubit, which is realized as a tiny LC superconducting circuit. Then to construct, let's say, Sycamore, which is the 54-bit, we pack these 54 of these in some fixed arrangement and get this fabrication, which is about the size of 100 fills. It's tiny. However, in order to maintain the operational state of the processor, it needs to be mounted in a cryostat. This monstrosity shown here is a cryostat, and this small processor is placed right at the bottom where it operates at close to freezing temperatures, just above 0 Kelvin. And there are other efforts from other companies and universities such as IBM, Intel, Honeywell, USTC China, that also produce their own designs with differing number of qubits. Generally, the more qubits you have, the more expressive are the problems that you can solve. In order to illustrate the power of such a processor, an experiment was conducted using the Sycamore quantum processor, which solved a particular problem in 200 seconds. And the authors argued that such an experiment on a classical supercomputer with 1 million cores would take, on average, 10,000 years to complete. So this is a huge difference, of course, but there's a caveat, which I'm not going to go over here, but the speed up is justifiable. There is a speed up. Okay, so quantum computing seems to do a lot of things a lot faster than a classical computer, but does not replace a classical computer. It assists in different ways. And here are some other useful applications of quantum computation, which researchers are looking forward to. So, for example, we have accurate high-energy physics simulations, chemistry simulations, material science, more efficient generative machine learning, fast real-time optimization and risk analysis for financial portfolios. So a lot of these tasks, they are doable on classical computers, but they are really slow. Quantum computation would accelerate this in a much and makes this a more feasible set of tasks that we can accomplish. But while quantum computers do have their advantages, they do pose some risk to the current cybersecurity mechanisms and policies that are deployed. And here I'll just mention two such risks. So first is the threat to private and secure digital communication. Current widely deployed encryption digital signature schemes such as RSA, ECDSA, and DSA, they are secure against attacks mounted by classical computers. Against secure is in quotes. But so, for example, if you look at the secure link between a client and, let's say, a bank server, the information exchange is protected using these protocols against normal computers, even perhaps supercomputers. However, a quantum attack can successfully break such protocols in a vastly shorter amount of time. So some researchers they found that in around 8 hours or so they could break RSA using an ideal quantum attack, and I'll explain what ideal later is. So using a quantum attack, we are able to break this encryption, read all the confidential information that is occurring between you and your bank, perhaps even modify things that might not be authorized. So this is dangerous. So this is the first risk. Another possible threat is with respect to passwords. So current password protection mechanisms, they use hash-based algorithms such as SHA-2, 3, and they are secure against traditional brute force attacks. But an attacker that has a quantum computer at their disposal, they can actually speed up the search to recover the right password. Now I'm saying here, like the thing is, like, you should have access to this hashed list of password in the first place in order to mount such an attack. But once you do have this quantum computer and you have this hashed passwords file, you're able to recover one or more passwords from this file. Okay, so these are two risks. There are other risks that I will unfortunately not have time to talk about in much detail, but this is something that we should consider. But should we? So is this thing, do we really need to worry about such a quantum computer, especially since only small selective companies or organizations, they have access to it. Well, large-scale quantum computers still have a long way to be fully realizable by the general public and be at a stage where they pose a realistic risk to security. So you need around 1 million noisy qubits in order to, say, break the security protocols that are currently being used, say, between banks or governments. Scientists claim that we may reach such a point in about a decade or so. Okay, but this still does not mean that we're protected. So sure, we're protected against individual attackers, lone adversaries, but we can't say anything about governments or adversarial, organizations that have access to a large amount of resources, monetary resources, and could purchase such a quantum computer. It's quite feasible. So governments need to, I think, are perhaps the most vulnerable to such a thing. So we need to be proactive and prepare for when such a time occurs or comes. All right. So as a result, here are some possible future directions that we can look at in order to be prepared for such an eventuality. So quantum computers, researchers say that it's an inevitable evolution of classical computers, but perhaps will not replace them, but they will be used in concert with them. So we still need to prepare for this eventuality. So one thing that we can do is we need to develop quantum resilient encryption mechanisms. And there are such quantum resilient mechanisms that are being researched. So us cryptographers are already researching such methods, which lies in the realm of something called post-quantum cryptography. You'll find things there such as lattice and isogeny-based public key encryption. Another thing is that let's try not to use a quantum computer to break things, let's try it to build new things. So let's try to develop new security mechanisms and applications. And people are doing that. So in theory, they are doing that. So they are developing random number generation protocols, key distribution protocols that allows you to use quantum computers to transfer two keys, sort of like a teleportation mechanisms, without damaging the security or the confidentiality of these keys. And finally, and perhaps arguably the most important point, is that governments, industry, financial organizations, cloud service providers, they need to prepare to upgrade their infrastructure. Perhaps not immediately, but eventually this is going to happen, and this transition is not inexpensive. So this transition should be taken into consideration, perhaps put in like in a long-term plan, to consider that quantum computers are a possible threat, and we need to consider them as part of as part of the post-quantum transition towards post-quantum resilience. So we're going to see, if you want to do that, you can actually see NIST standards for guidelines, which they already talk about the standards that are necessary in order to go towards this quantum secure world. I think that's it for me. So thank you very much for giving me the opportunity to present here. And I think I'll leave it to you, Aisha. Thank you very much.